Every engineering organization eventually hits a wall where a platform that was once a showpiece rusts into a liability. Release velocity drops, and the backlog fills with microscopic fixes that barely move the needle. Engineers push a boulder of legacy complexity up a hill, only to watch it roll down. A team invests a year in a cleanup, feeling lighter briefly. Then, feature pressure reaccumulates the debt. The boulder resets. The push begins again. For 30 years, the industry answer has been to refactor incrementally and avoid a total rewrite. This dogma was born from the high-profile failures of the late 90s. When Netscape attempted to rebuild its browser from scratch, it lost its market position, creating a historical trauma that trained engineers to view rewrites as a primary strategic risk. The Fowler doctrine of refactoring became the standard, favoring small, safe, reversible transformations that allowed business operations to continue without a multi-year pause. This approach reflected the reality of human labor. Rewriting a massive system with a human team took twice the time and required resources that could not be spared from new feature work. Choosing to refactor was a rational financial defense against the extremely high cost and low predictability of manual code production. By 2026, frontier model orchestration and the hybrid engineering bench have shifted the baseline. The economic constants of software production have inverted over the last 18 months. For a clearly specified component, the cost curve for generating a fresh, well-tested implementation has dropped by roughly an order of magnitude. Contrast this directly with classical refactoring, where the labor-intensive process of untangling legacy code ensures that the cost remains high. Rebuilding is now the default economic answer, while refactoring has become the extremely expensive fallback that requires specific justification. This forces a question for every engineering leader. Why apply the logic of the early 2000s to the production function of 2026? Defending the refactor default in this new environment is a measurable financial error caused strictly by relying on outdated heuristics. To see the impact of this shift, consider a standard 150,000-line back-end service with a 10-year history. This comparison matrix from 2026 field reports shows the gap. A classical rolling refactor on this size service typically requires 18 to 36 months. An agent-driven rebuild completes the same scope in 8 to 16 weeks. Resource requirements also shift from a dedicated team of 6 to 8 engineers to a pair of conductors. This speed is enabled by the collapse in the cost of producing code, extracting intent from legacy repositories, and running high-fidelity evaluation suites. The most significant factor in this calculation is the opportunity cost. A multi-year refactor cycle prevents a team from shipping new product capabilities or pursuing the strategic bets that drive long-term value. Choosing a 3-year refactor cycle over a 6-month rebuild effectively deprives the business of its strategic agility for the duration of the project. Even a successful refactoring program carries hidden penalties because it is designed to preserve the existing system's traits. There are 3 structural taxes a refactor cannot discharge. First, inherited pragmatism forces the team to carry forward every quirky workaround. Second, shadow intent remains trapped in the code, requiring a permanent priesthood of engineers. Third, migration fatigue locks the team into endless framework upgrades that consume throughput without delivering value. A rebuild resets this clock, allowing the organization to intentionally discard obsolete behavior and update the system's specification for current needs. Refactoring merely slows the bleed of a legacy system, while rebuilding allows the team to return to a net product focus. Many organizations still avoid rebuilds out of a fear of losing mission-critical, undocumented business logic. The solution is intent archaeology, a systematic process for reverse engineering a system's true contract. Machines map the repository in hours. Behavioral replay captures production traffic to create an honest record of real-world responses. Human engineers then triangulate these findings through structured interviews, filtering out accidental bugs to ensure deliberate intent is carried forward. This produces the archaeological record, a pristine blueprint that describes what the system actually does and what it was intended to do. We have reached a point where legacy modernization is no longer limited by coding velocity, but by our ability to extract intent from existing code. When these service-level inefficiencies are scaled across an entire organization, the impact is immense. Research suggests that enterprises spend 40 to 60% of their entire IT budgets on the simple maintenance of legacy systems. An agentic rebuild discharges this migration debt for the targeted scope, allowing that capacity to be reallocated back to R&D. This creates a new mandate for platform planning. If your modernization business case still uses the cost curves of the pre-agentic era, the case is wrong. Relying on those old numbers will lead to uncompetitive resource allocation and a widening gap against competitors who have updated their arithmetic. Engineering leaders can now move past the cycle of maintenance, using machines to replace the hill of legacy debt with an entirely new landscape.